Hello friends, I welcome you all in my series of lectures on radar engineering. So in this series, we are going to see today about radar range equation. Now, to derive the radar range equation, consider a radar using a transmitting antenna which radiates the power uniformly in all directions. Such an antenna which is radiating power in all directions is called as the isotropic antenna. So let Pt be the power radiated by such an antenna. When the power density at a distance r is given by power density from the isotropic antenna is equal to Pt upon 4 pi r square. But many times we know the direction of the target. So if you know the direction of the target, we can use a directive antenna. Now, if you are using a directive antenna, we have to add the parameters of the directive antenna in this equation. And then we can rewrite the equation like power density from the directive antenna is equal to PTG upon 4 pi r square, where G is the gain of this directive antenna. The amount of power which we are transmitting from this radar towards the target is given by PTG upon 4 pi r square. Now this power is intercepted by the target. Now this power will illuminate the some area or some part of the target, and that particular area illuminated by this transmitted power, that is called as a cross-sectional area. So the amount of power intercepted by the target at a distance r from the radar is given as P equals to PD sigma up is equal to PTG sigma upon 4 pi r square, where PD is the power density and sigma is a cross-sectional area. Now, when this power falls on the target or a target intercepts this portion of the radiated power or incident power, then target will not going to absorb all these incident powers. So, what the target will do? It will radiate or it will re-radiate the power in various directions. Now, as the target is re-radiating the power in the various directions, then the measure of this amount of the incident power intercepted by the target and re-radiated back in the direction of a radar is denoted as radar cross-section area, and it is indicated as a power density which is re-radiated backward, that is also called as echo signal at a radar, that is equal to PTG upon 4 pi r square into sigma upon 4 pi r square, where radar cross-section area sigma is having all units of area at it is the power occupied in the all directions or the various directions. Then radar, when this power which is re-radiated backward towards the radar antenna captures the portion of this power, and how much power is captured, how much power captured by this radar antenna, that depends upon the effective area of this antenna. That is, effective area is indicated by AE, and the power PR received at a radar is given as PR is equal to PTG upon 4 pi r square into sigma upon 4 pi r square into AE, that is equal to PTGAE sigma upon 4 pi square r raised to 4. So that is the total power received at a radar with the antenna having effective area AE. Okay. Now, from this power, we can find out the maximum range where we can detect the target. So maximum radar range, it is indicated by Rmax, and it is the distance beyond which the target cannot be detected, and it occurs when the received echo signal power PR is just equal to minimum detectable signal S minimum. Now this S minimum can be calculated as just by replacing PR by S minimum, and that is equal R by R max. So that is equal to PTG sigma upon 4 pi square R max raised to 4. Now we can find out the maximum radar range equation by rearranging the terms of this equation. It is indicated as the Rmax. So Rmax is equal to PTG sigma upon 4 pi square S minimum raised to 1 by 4, and this is the fundamental form of a radar equation. So in this fundamental form of a radar equation we are having two antenna variables, that is G, that is gain of antenna, and AE, which is the effective area of the antenna. But the G and AE are related to each other like this: G is equal to 4 pi AE upon lambda square. So in this equation we can replace G by AE by using this equation, or we can replace AE by G by using this equation. So at the place of G we can write 4 pi AE upon lambda square in the equation, and we can write the equation in the form of AE only, or at the place of AE we can write G lambda square upon 4 pi, and we can write this equation in the form of G only. So these two forms of the equations can be written like this, that is R max is equal to Pt g square lambda square sigma upon 4 pi cube S minimum whole raised to 1 by 4, or R max is equal to Pt A square sigma upon 4 pi lambda square S minimum raised to 1 by 4. So these are the two another form of a radar range equation, where Pt is the transmitted power in watts, G is the antenna gain, A is the antenna effective aperture area, that is in meter square, sigma is the radar cross section area, that is also in meter square, and S minimum is the minimum detectable signal at a range R max, and that is in watts. So this completes a radar range equation. Thank you.